Well, hi again, and welcome to Lecture 4 of the second half of Physics 3113, Thermal Physics and Statistical Mechanics. And I'm Tim Duty, your lecturer for the second half of the course. In this lecture, we're going to use what we derived in the last lecture, that is canonical ensemble and its properties. And we'll use that to study a type of paramagnetism. To be more specific, it will be paramagnetism of localized moments. And that's where we imagine that we have atomic magnetic moments or atomic spins due to the orbits of electrons that are localized on lattice sites in a solid. But first I would just like to review a couple of things we introduced and discussed last time. I introduced the canonical ensemble, and we found that when we had a system connected to a very large heat bath, we could write the probabilities for finding a system in energy level with energy epsilon sub I in this form, e to the minus beta epsilon sub I, and the normalization z, which is the partition function, which is a sum of over all the states of these exponential factors. And we showed that once we had the partition function, we could determine important quantities such as the mean energy, which is easy to see that it's the partial derivative of the logarithm of the partition function with respect to beta. Beta being, of course, 1 over kBt. That's easy to see just by plugging this into this equation. In later lectures, we'll see that with this partition function, once we have the partition function z, we can get a number of quantities. For example, we can find the mean fluctuation in energy given by this derivative, which is, as you'll see, is a second derivative of the partition function, or Helmholtz potential. And in other systems, we'll see if we can find, for example, the pressure. Now, in the last lecture, we defined an energy F such that the partition function z could be considered to be the exponential of minus beta times f. In other words, this f equals minus kBt, actually it should be a kb there, kBt, logarithm of the partition function. And this, of course, is known as the Helmholtz potential, or otherwise it's called as the Helmholtz free energy. Now, I kind of implicitly talked about intensive versus extensive variables in the last lecture, and I just wanted to go over that again to make it a bit more clear. So for now, we're going to explicitly look at the canonical ensemble for n non-interacting identical systems. That is, we have n copies of the same system, and this system has r energy levels. Let's call this system 1. And it has r energy levels labeled by epsilon sub I, r energy levels, and we'll label them by I. So our partition function for this one system will denote z sub 1. That's going to equal the sum over I. I is going to go from 1 to r. I'm trying to be a bit more explicit here, of the exponential of minus beta epsilon sub I. Well, suppose we make a system by putting together n copies of this system 1, identical copies. Now, at this point, we should say they are distinguishable copies. They're distinguishable systems, since later in the course we'll have to consider the situation we have in quantum mechanics when we have indistinguishable particles. That we'll do later in the course. But for now, you can think of them, even this could be a quantum system, you can think of them as being distinguishable. And that's because they sit on different lattice sites. Well, it's pretty easy to write down the partition function for the system of n copies. We could write it down, we could start this way and write it down by every energy level of every constituent of this has an exponential term. So we'd have this big sum where we have to sum over each copy. So sum over I, j, and down here we would have, n of these summation variables, and each one would go to r because they're identical, and we would have the energies, because the energies add, because they're not interacting, the energies are additive, and we'd get something that looks really very big and hard to work with, but it's pretty easy to see because we can factor all these, because the energies are additive, because these do not interact with each other, that Z sub n is just this quantity raised to the n power, and you get all these terms. In other words, Z sub n, the partition function of the system with n copies, is just Z1 raised to the power n. And so if we take the logarithm, we see, of course, log Z sub n is n times log Z sub 1. That's pretty easy to see. Just go and just sort of think about how that comes out. Okay, so we see that we can also see that the total mean energy for the system with n copies is n times the mean energy of one system, this little u here. So use the mean energy of a single system with r levels. Likewise, we have the entropy as additive as well. So the entropy of the large system with n copies is going to be n times this little s, where s is this Shannon entropy, where we just sum over the levels of one system. So we sum over the probabilities with I going from 1 to r. So we see that little u and little s are intensive, while big U and big S are extensive. And we can also see this for the Helmholtz potential. We'll just call F, we'll drop the subscript here, but F sub n is just n times the free energy of one system, a system of a single system with r levels. And so we can write that this way, of course. Okay, so now let's look at the entropy, this small s, the entropy of one system, one isolated system with r levels. Well, we've seen before it has this form, minus Boltzmann's constant times the sum. And if we just plug it, we of course recognize this term as the logarithm of Z1. Right, so if we take, so these two, let me just say that again. We plug in this little pi, which we know from here, right? It's just, well, it's, do I have it written down? Let's see if I have it written down. Well, yeah, here, right? This, except we're calling this system Z1. Anyway, if you just take this term and take its, or p of I, and take its logarithm, you get these two terms here. Well, you get a minus sign, and we've canceled the minus sign out here, but we get this equation here. And now, of course, because this doesn't depend upon I, we can pull this outside the sum, and we can break this into the two terms where we just have the sum over variables that depend upon I here. And of course, that's just going to be equal to 1. And this we should recognize as the average energy of one system, this little u, the expectation of little u. So in the end, we can write this small entropy in this form if we wanted to. Or if we multiplied by n, we could have the entropy of the total system of n copies, large n copies, could be written like this. Capital S equals kb log z sub n plus beta kb, and the expectation of the energy of the system with n copies. Well, that's a nice form to write down the entropy, because we could multiply this equation by both sides of this equation. Let's multiply that by temperature, T, and of course what we see is that we have, that leads us to Ts is minus F, so T times this is just minus the Helmholtz free energy, this one, plus beta times the expectation of large U. Or if we solve this for the free energy, we have F equals the expectation of large U minus Ts. And this is indeed, we recognize this as indeed the definition of the Helmholtz free energy from classic thermodynamics. That's pretty straightforward. Okay, let's just think about classic thermodynamics again. And in classic thermodynamics, the entropy of an isolated system depends upon the variables total energy, volume, and N, the number of items or atoms or particles. And these are independent variables, that is U, V, and N. They're considered to be independent variables, such that the entropy is a function of U, V, and N. So this is, once again, and this is an isolated system. For an isolated system, classic thermodynamics. Now, in classic thermodynamics, if we have a closed thermodynamic system that's held at a constant temperature, T, then T becomes an independent variable, or in other words, a control parameter. And so we accomplish this by a change of variables, and this change of variables is handled by a Legendre transformation. So I think you probably had this in the first part of the course, F equals U minus TS. So we see again how this canonical ensemble, that is a system in contact with a heat bath at fixed temperature T, corresponds to classic thermodynamics at fixed temperature, right? So we had, from the statistical approach, we had this. And the idea is when N gets very, very large, we can replace, we don't have to worry that this is a mean value. Because, and then we'll see this in a later lecture, that as N, in systems like this, when N gets very large, the fluctuations in these quantities get very, very small. So that's the correspondence between canonical ensemble and classical thermodynamics. Okay. And I hope this actually clarifies the meaning a bit of intensive versus extensive variables. So have a look at that. Okay, well now we're ready to move on to something interesting. We can use all this machinery that we've developed, and we can start to calculate some interesting things. So the first system we'll study is a collection of localized spins. And we'll study paramagnetism of these localized spins. So we can consider a collection of N, let's say spin J atoms. We'll be a little bit general here. So we could just study spin 1/2, but we'll make it more general to start with. So we know in a magnetic field, each atom has a Zeeman interaction energy, and it's written usually as minus mu dot B, where B is the magnetic field and mu is a magnetic moment. Here, B is a local magnetic field, and it acts on a sort of magnetic dipole, mu. Mu is a vector quantity, and mu is given by this G factor times the Bohr magneton times the spin vector J. So if you remember, if you had physics 2.114, that the magnetic field can be written, B can be written as the contribution of the applied field H, or mu naught times the applied field H plus M, where M is the magnetization. So in this derivation, we're going to assume the concentration of paramagnetic spins, the spin J atoms. We'll assume the concentration is very, very small, so we'll kind of ignore the magnetization, the bulk magnetization of these, that is the effect of the magnetization on the magnetic field, and we'll just take the magnetic field to be mu naught H. We don't have to do this, but for this derivation, we'll do this. Now, just a note about notation, mu, which is in bold, which means it's a vector here, it's not the chemical potential. It's a magnetic dipole moment. We will get to the chemical potential, and we'll use mu for that. So there's an opportunity here to get confused, and it's just because we don't have enough letters, Greek letters and Latin letters. But in this lecture, mu will be the magnetic dipole moment of one of the spins. So if we have a field directed along the z-axis, the Hamiltonian is given by this term. We write H is minus G mu sub B, where the B here stands for Bohr magneton. That's what the B there stands for. And we know what the Bohr magneton is. It's E h bar over quantity 2 mass of electrons times C. And it's times the magnetic field, and then we'll sum over all of our spins, we have capital N of them, times this spin operator, J, I, Z. So this doesn't mean to the Z power, this means the I spin, the Z component of J of the I spin. That's what that means. And so all these can in principle be different values of J given by, well, we'll come to that, but this is our Hamiltonian. So in quantum mechanics, one finds when we have a spin J atom that it can take on two J minus 1 values. That is this, and these can be labeled by M, and if those two J plus 1 values go from minus J up to plus J, so minus J plus 1, minus J plus 2, all the way up to J, that's 2J plus 1 values. And those have energies, we'll denote them epsilon sub M, which are minus G times the Bohr magneton times M, this M, times B. So our M indices are going to go from minus J to J. I mean, before we were using indices 1 to R or something, but it doesn't matter. That's fine to label them this way. The main thing is they have energies that are a function of this M, like so. And of course, we'll assume our spins are in contact with a heat bath. And, well, you can ask yourself where this comes from. And, for example, if we're talking about atomic spins on lattices, well, they exist in a solid and they couple to lattice vibrations and so forth and so on. We won't specify that. That's the beauty of, I mean, at some point you might be very, very interested in that. But we'll just think that this environment forms a heat bath at temperature T. So we'll use the canonical ensemble. And of course, the number of spins here will be fixed. And since the spins sit on a lattice, the spins, which are atomic spins, will be distinguishable. Like I said, later in the course, we'll worry about indistinguishable particles. We'll see we have to be a little bit careful with that, especially when we get to Bose-Einstein condensation and Fermi gases and so forth. But for now, we can take them to be distinguishable. Okay, so there you go. So we have everything really we need to do. We just have to kind of do the sums and find the partition function and so forth and so on. So let's do that. And just once again, as I said at the beginning of this lecture, for distinguishable particles, for example, spins on a lattice that are non-interacting, the probabilities and partition function factorize, just as we showed. So here it is written with the probabilities, which is easy to see since the energies are additive. That's the fact that the energies are additive means there's no coupling terms between the spins, which you will get to later in the program in physics. Probably not in this course, but in if you take honors statistical physics. But anyway, they're non-interacting, and so the total energy of the system are specified by this collection of integers m1, m2, all the way up to m sub n, and all these go from minus j to plus j. Right? So we could write down the probabilities if we want. And so actually we could write down the probability of a single spin. Let's focus on one of them since they're all identical and we showed how to handle large n copies of the same system. Well, the probability of one of them is given by this kind of term. Or we can write Z1 is just, we sum m from minus j to j of these exponential Boltzmann factors, we call them. So we have beta, g mu b, m, which is this value, times the strength of the magnetic field. And of course we see here that z sub n is z1 to the nth power, as we showed before. So we can get everything, and this one is really easy. We get everything by just finding the partition function for one spin, which is this. And that's how it works for non-interacting spins. It's relatively simple. Now, note that the mean Z component of the magnetic moment of an atom, we'll call that mu bar, is given by this sum. So this is just a sum over the probabilities of being in, of that one atom having magnetic moment given by m times the magnetic moment, right? So this is just, so that's how you get an expectation value as we saw before. And if you look at that, you can work out that this equation, I mean, in principle, you could find it by doing this big sum, but the nice thing about the partition function is you can see just by plugging in the logarithm of Z1 here that mu bar is 1 over beta times the partial derivative of the logarithm of Z1 with respect to the magnetic field, beta. You see how that works? When I take those derivatives, I pull out, when an exponential, I pull out this term times the same exponential out front. So you can see how that works. Just plug it in and try it yourself. So the point being that is, if we find a really simple form for this partition function, Z1, I mean, this having a sum is not that simple usually to work with. I mean, you can, but if we can find a form for this that's easier for us to work with, we just have to take this partial derivative and divide by beta, and we have the average magnetic moment, Z component of the magnetic moment. So let's calculate Z1. Let's define this variable eta to be, which is a dimensionless variable. It's minus beta times epsilon sub m, right? Let's see. I should, did I get that right? This should be, eta is epsilon of 1 is what I actually meant here. So we get this term. So if we plug in minus, if we take m of minus 1, we get this energy scale. What we're trying to do is get an energy scale associated with these levels. The levels here are all separated by some spacing, and that's what this is. So this should be epsilon minus 1, let's say. And we see it's just equal to beta g mu bb, that's dimensionless, or writing it out in terms of kbt, we have this. This should be kb, by the way. So what the point of doing this is, this eta is a dimensionless ratio of magnetic to thermal energy. So it's a measure of the competition between alignment due to magnetic energy and randomization due to thermal energy. We'll see how that works. So then we have Z1 is, that simplifies our sum a bit, because now we can just write Z1 as the sum over these terms e to the eta m. We still sum from minus j to j, and so we have a bunch of terms like this, right? We have 2j plus 1 terms. And if you have a sum of terms like this over an exponential, you should recognize that this is a finite geometric series, has a finite number of terms, and you can actually sum this, and you'll get this answer here, summing a geometric series. And you can just rewrite that by shifting things around a bit to this function. So here we've found z sub 1, and it really has this quite simple form. It's the hyperbolic sine of j plus 1/2 times eta divided by the hyperbolic sine of eta divided by 2. So now, the logarithm of the partition function, well, we take the log of that, and I've got people sending me email about my devices. Okay, sorry about that. Yeah, okay, that doesn't look too simple, but in fact, it helps us to evaluate this derivative. And of course, we want to take it with respect to beta. Remember, we found this relation. And of course, we have this in terms of eta. Well, it's just some change of variables or using partial derivatives. And we can write then mu bar in terms of the partial derivative of the log of the partition function of one spin with respect to eta. And we have this. And so that's actually not hard to do. It doesn't look so neat actually, but it's really about as simple as it can get. We find that the average magnetic moment, Z component of the magnetic moment, is G times mu B, right? That has the right units of magnetic moment, times this function here, which of course is dimensionless, right? And you look at that function, and of course if you wanted to, you could go and plot that function if you wanted, which we will do. But it's kind of conventional. Of course, this was derived some time ago. It's conventional to lump all this stuff here in the brackets. Well, actually to pull out J and lump the rest of the stuff in this kind of script B sub J function, because it depends upon J. So this in the brackets divided by J is called this so-called Brillouin function, right? That's what it's known as. And you can see that if we actually studied the special case of spin 1/2, this Brillouin function would be simply the hyperbolic tangent of eta over 2. Okay, so we've worked out the average magnetization of a single spin. And of course, it's easy to cover the case of a large number of spins. So if we have, let's call it N0 atoms per unit volume, then the mean magnetic moment per unit volume, which you might remember, maybe you don't, but I'll remind you, the mean magnetic moment per unit volume is what we call a magnetization, right? If you remember from the introduction to electrodynamics in second year, that is precisely the magnetization, mean magnetic moment per unit volume. So we just multiply the density of atoms per unit volume times the average magnetic moment per spin, and we get the magnetization here, M here. And so we see this, it's N0, G, the Bohr magneton times J times this Brillouin function. And I've actually plotted this, I've actually done this and plotted this Brillouin function for different spins. So for spin 1/2, which is just, of course, the hyperbolic tangent function. And you can see for higher spins, it just becomes a bit steeper there. And this is a function of this eta. So remember, this eta is the ratio of magnetic to thermal energy, right? This is eta. And so, of course, what you see, if the magnetic energy wins, the Brillouin function is very, very large, is 1, and the magnetization is saturated. And if you're down in this regime, though, when the magnetic energy is small compared to the thermal energy, then the magnetization is actually, which is proportional to the Brillouin function, is linear with inverse temperature, right? Because this goes like eta goes like 1 over kBt. Let's see, what eta was here. Goes like, eta goes like 1 over kBt, it goes like beta. Anyway, well, and that's just what I said. So, and you can do this mathematically. So for small eta, that is high temperature limit, the magnetic energy is much, much smaller than the thermal energy. The temperature is high, kBt is large compared to the magnetic energy, which is this G mu B times B. Say, what was magnetic energy? Let's go back to that. I should have wrote it on that page. Magnetic energy is G mu B times the magnetic field, right? Anyway, the high temperature limit means this eta is small, and it's very easy to find that the Brillouin function in this limit, small eta, is just 1/3 J plus 1 times eta, right? That's what it's linear. And you can write this, of course, in kBt. And so in this high temperature limit, the magnetization is it's inversely proportional to the temperature, and it has actually this form, right? So the magnetization is inversely proportional to the temperature. Sorry, this K should have a B. In a lot of these slides, I sometimes drop the sub B for Boltzmann constant because you write it all the time, and then at least if there's no confusion, K is usually Boltzmann's constant. So I hope that doesn't confuse you. And the B here, of course, is not Boltzmann, it's Brillouin. So we have to, it's always, we need to make sure we understand the notation. But anyway, what you can see is in the high temperature limit, magnetization inversely proportional to temperature and proportional to magnetic field, or H here. Well, I put the mu naught H here for B. And the constant of proportionality can be derived, can be found. And it's also proportional to the spin squared, J plus 1. Okay? Well, you can also see, oh yeah, and so, yeah, that's exactly what I just said. It's proportional to eta, proportional to B over T, magnetic field. And so if we take the susceptibility, remember the susceptibility, we usually say if M is proportional to H, then we call that susceptibility, and this allows us to read off in this limit the susceptibility right away. And so this temperature dependence of susceptibility you may have seen before, it's known as Curry's law. When susceptibility goes like some constant C over T, named after Pierre Curie. So, and this Curie constant we've derived here. And I think there's actually a lab, third-year lab, where you discuss this constant here. You try to measure it from some magnetic materials. So what we've derived then is the susceptibility of localized moments, so the paramagnetism of localized moments, and we use the canonical ensemble. Now we can look at the other limit, the low temperature limit. So that's when the magnetic energy wins out, then the magnetization saturates to this value here. And of course, the other very interesting thing to look at once we have this is what's called the heat capacity. In fact, we'll look at the heat capacity per unit volume. That's just the number of spins per unit volume times the heat capacity of this little c of a single spin. And the heat capacity is this derivative here, this little cv. And so it's easy to work that out, well, remember the average energy is given by this derivative of the partition, of the log of the partition function. And so we can actually, so what we're trying to do is we're trying to find this mean U1. We find that in terms of what we've worked out now. Just by we use this eta. This is just changing, from beta to eta. And then once we have that, we just take this derivative with respect to t. And so let's just make it simple. So we have this. We still have this Brillouin function. So let's just consider j equal 1/2, where the Brillouin function is this easy function. And what you can see then is you can derive the heat capacity, and it has this form. And we can write this. I apologize, I'll have to fix this before I upload the notes. I got cut off here. But we can write the heat capacity. And now this is this magnetic energy that I wrote as G mu B times B. I'll fix that when I post the lecture notes. But let's just plot it. So I'm going to plot it with respect to x, which is the inverse of my eta, basically. I know it sounds funny, but it looks better plotted this way. So we're going to plot the heat capacity per unit volume as a function of temperature, basically. And we're going to make the scale here unitless by taking this magnetic energy, this is our magnetic energy squared, of course. So this is 1 over the variable we called eta, but I want to plot it as a function of temperature, is why I chose to do this. And so what you can see then And we're going to scale the heat capacity by, we're going to look at the heat capacity per unit spin, because we just have to multiply by N0 to get the heat capacity per unit volume, so it's kind of trivial. And we'll scale our heat capacity by kb over 2, right? Boltzmann constant divided by 2, right? Because usually we expect, for example, an ideal gas, a system with 1 degree of freedom, classically, we would expect that in classical thermodynamics, we would expect that to be something like, kb over 2, right? Or 1 in this units. And so you can see the heat capacity starts out at low temperatures at 0, and it builds up and it has some peak, and then it falls off. And you can actually see that it falls off here like x. So it falls off like t squared, right? Just comes from this, because when x is really, really large, that's 1, and this just falls off like that. Now what I want you to ask and think about when you're going through the derivation here is, do you understand why it goes to 0 at both high and low temperatures? Can you describe that in words and not just equations, but give me a sort of qualitative description of why that happens? That would be good, and we might come back to that. Okay. The other thing I want you to think about is we derived this for magnetic moments or magnetic dipoles. What about if we wanted to work out the problem of dielectrics? That is where you have electric dipoles in electric field. So for example, like a dielectric between in between plates of a parallel plate capacitor, let's say, or any capacitor, and electric polarization, which you also had in second year electricity and magnetism. So what do you think? How hard would that be based on what you've seen now? What would you expect for the temperature dependence of that? Okay, I'll leave you with those thoughts, and that finishes lecture 4, and we'll do some more calculations with this in the next lecture. Okay.